Good morning, good afternoon, good evening, depending on where you are for this hybrid virtual conference. My research for today is entitled Optimization Techniques for P-GTO Thyristor Design. The objective of this research are listed here. By design, we wanted to obtain higher possible control voltage between gate and cathode of the thyristor, leading to higher blocking anode current and lower turn-off time. An outline of the work starts with fabrication process, continuing with gate-cathode junction optimization by using doping and also beveling of the junction, then obtaining the maximum voltage at the gate-cathode junction, also obtaining the anode-to-cathode maximum voltage for the device, and finally obtaining results about switching characteristics. The anode was realized on silicon wafer doped with boron, so P-type. And then we have an epitaxial growth of N base, 2 microns layer, phosphorus concentration, and P base, thick P base of 23 microns, epitaxial growth of silicon layer doped with low concentration boron connected to the gate. We will see later the doping profile for the device. Second stage of fabrication process is for the cathode, 0.2 microns, silicon layer highly doped with phosphorus, so N-type. The cathode gate junction is configured by lithographic process and anisotropic etching. We will see also the configuration for the cathode gate junction. And the next process step is aluminum layer deposition, patterned for cathode and gate electrodes. In this picture, we have the structure for gate-cathode junction. We can see the materials into the device with yellow silicon, basic semiconductor material. Blue is the silicon oxide used to separate and passivate the junction of the cathode. In pink and blue, aluminum electrodes for the gate and for cathode. Gate is to the right, upper right, and cathode is upper left. In this figure, we see again the configuration for gate-cathode junction. But this time it is shown the electric field intensity of the structure. With violet color is the lowest field starting from 0, and with red color is the highest value of the electric field intensity, up to 2 times 10 to 5 volts per centimeter. We can see in this figure that below the gate terminal, upper right, the field intensity is bigger. So objective of the optimization was to lower the field in this region by doping and by beveling. In these drawings, we see the doping profiles of two devices. In the left side, there is the PNPN structure of the classic GTO thyristor with a low doped N base. And to the right, we see the doping profile for the new P- GTO, which has a low doped P base. The cathode in these pictures is to the left. So we have PN right to the left. Now let's see some results. Obtained the maximum breakdown voltage of the gate-cathode junction of the classic GTO was obtained 9 volts. This was simulated from the examples of simulation program, TCAD. And then what we did is to replace in that circuit the classic GTO with the new P- GTO, and we obtained a maximum breakdown voltage of 14.5 volts, which represents an increase of more than 50% in value. Moreover, we afterwards did the gate-cathode junction optimization of the P- GTO structure by beveling and obtained value of the breakdown voltage 27 volts in the case of positive bevel, so even greater value. Regarding the voltage, maximum voltage for anode-cathode terminals, we have in these figures the reverse characteristics for the classic GTO to the left and to the right for new P- GTO. We can see two things here. The new GTO has an increased breakdown voltage of 340 volts compared to the classic one, 240 volts. And also, the characteristic shows that for the blocking region, the reverse current is lower for the P- GTO, which is a good thing, is desirable. We have here the results in figures. So P- GTO versus classic GTO, maximum anode to cathode voltage. And we can make an observation that since the doping of the high resistive base of the devices was the same, we saw that in the picture with the PNP doping profiles, this gain of voltage is due entirely to the novel structure of P- GTO. About switching characteristics, the result is that the turn-off time is similar in both cases on both devices. But considering supplementary that in fact for P- GTO, a larger turn-off control voltage can be applied on the gate terminal. We see 27 volts compared to 14 volts or 9 volts. So the P- GTO device exhibits superior switching characteristics. In conclusion, design optimization techniques applied with Silvaco TCAD simulation tools lead to improved static and dynamic characteristics of the P- GTO thyristor. The main advantages are augmented breakdown voltages of the power device and faster turn-off switching. Thank you for your attention.